Asbury? Yep. Okay.
I'm wearing red, it's just under this.
Okay.
It's a red shirt.
You read my mind. Let's see. Tudor? Let's see. Burdette? No Burdette yet. Richardson. That's right. Rice. Okay. Polly? Midkiff? And let's see. Burdette? No, I said that, didn't I? Hemmings? No. I did better Wednesday than I'm doing today. Taylor. Okay. Got Van Cross online. Michaela's not here yet. Reed? Redmond? No Redmond yet, huh? Oh, yeah, okay. I thought that was you. Hemmings, Bowers, Felder.
Here.
Felder's online. Hudson's online. Burdette is online. No Newton yet. No Massey yet. No Cedric yet. No Pauly. No Butler. Derek is online. Sipple. That's right. Got you. Hodges isn't here yet. Is everybody accounted for? Anybody here I didn't call? I think I got everybody online. Not that it matters. For those of you online, oh, Michaela's here. Speaking of online, technically I don't need to write down who's online, obviously, because one, you're going to be required to send me the words as you usually do, and then also Google automatically gives me a list of who showed up online and what time they logged in and what time they logged out. You might be wondering why you have to send the words in if that's the case, but the reason is it's because just because you're online doesn't mean you're actually paying attention. You could easily log in and go to sleep, or do what I do when I'm in a boring meeting, which is log in and do other stuff on my computer. I'll even keep my camera on so it looks like I'm paying attention, because I am paying attention to my screen. I'm just not paying attention to what they're saying. So I'm going to avoid remove that temptation from you by having you send in keywords. I'm punishing you for my own bad deeds. I apologize. All right, we are recording, so I guess I'll do some basic announcements because, again, even though not everybody's here yet, they can always watch and get the reminders. Let me think, because I want to do the least important ones. Independent work, obviously, as of Monday, you should have had 7.2 points worth of independent work. By this coming Monday, you should have 14.4 points of independent work. It will catch up on you. Find somebody who's had this class before, especially if they're taking it twice, especially if you're an athlete. I don't mean that in a bad way, but just because you guys know each other. So surely you know somebody who's had me before, and ask them. Like, it'll catch up to you. So you should really get started early, especially considering that right now everything is worth 18 points a page, right? That's a lot more than 10 points a page. So you have one of your classmates is almost done. They're in their 90s. And they haven't even written that much. They just watched all the movies that are out there so far, and they wrote a few pages. And, they're already almost done. So, take advantage of it while you can. I see Newton's online. Good morning, Newton. So yes, please do some independent work. Also, I don't think I even mentioned this. If you have other ideas for independent work, let me know. Because like we said, it's a writing thing, right? But as you can see, you can also watch videos. You can do the study guides. You can go to basketball games, right? All this other stuff I've been throwing out there. You can bring in crushed cans. Like I just I posted that announcement earlier this week, right? So there's all kinds of little things you can do for independent work. So if you have an idea of something I haven't listed or announced, let me know. I'm open for ideas. Speaking of independent work and other ways to get it, you guys should read your announcements. So a lot of times in my announcements, and I mentioned this on Wednesday, I'll say something in the announcement says, if you read this entire announcement, send me an email, reply to it. That way I know, one, I know you read the announcement, and two, if you do that, you get extra points. So all I'm asking you to do is read the announcements. I told you that you need to anyway, because it's important information coming out to you. But also now you're getting an incentive, right? I'm giving you points just for doing what you should be doing, which is reading the announcements. Of course, that being said, anything that I've already posted that said reply to this, if you see it, it's too late now, right? So every day when we move forward, the old ones expire. But anyway, I see Cedric's online as well. Good morning, Cedric. So any questions about that stuff? I think we're out of announcements. I'm actually I really hope to have time to fix them by going there and grade them. I haven't even been able to grade them yet. What else? Your pre-labs are due on Sunday. If you don't know where to find them, you don't know how to do them, let me know. I'm here to help. I think that's it. And it's almost 8:01, at which point we'll get started. So obviously, if you're online, you're going to need to send in the attendance keywords as usual. I'm not changing anything up yet. For those of you who are watching the video instead of online, again, just like I did on Wednesday, what you're going to need to do is send in the keywords, but also send in a screenshot when I tell you the keywords. Good morning. I got Massey here. And then we will now officially get started because it is now past 8:01. What? 1 second. Bowers, right? Hold on. Yeah, it is Bowers, right? Yeah. Okay. Anyway, yeah, so let's get started. And this is where we left off. Hold on a second. Slideshow, current slide. Let's do, for the first word for attendance, let's go ahead and start it. Let's say the first word is atomic. So if you're watching the video, not if you're online, but if you're watching the video and you're not live, then screenshot me pointing at the word atomic. That is what you need to send in with the word atomic. All right. So anyway, yeah, this is what we left off with, talking about atomic mass. Because before we talked about, or basically I was explaining the fact that hydrogen, just using that as an example, not that you need to know this. If you were to look at its atomic mass, it says 1.0008. Not because there's any hydrogen out there in the universe that has that mass, but because if you were to take all the hydrogens in the universe and average them up, that's how much they would weigh. Because most of them weigh 1. Very few of them weigh 2, and very, very few of them weigh 3. So if you were to take them all and measure and average that up, that's how much it would weigh. So for example, like if most people in this classroom weighed 100 pounds, and then he weighed 200 pounds, and I weighed 300 pounds, and we were to average us all together and say, what's the class average of the weight? And it would be like 100.002 or something like that, right? It's not that any of us in here weigh 100.002 pounds. It's just that because most of you weigh 100 pounds and he weighs 200 and I weigh 300, then that's the way the averages came out. Does that make sense? So that's what we're talking about with the atomic mass. And the only reason I wanted to refresh your memory of that is because that brings us to our next term that I haven't taught you yet, which is isotope. You need to know what an isotope is. That is an alternative mass form of an element. You can write that down if you want. But I think the better way to think of what an isotope is, it's like this. And let me remind you of something I said on Wednesday. If you change the number of protons, you change the element, right? So hydrogen has one proton. If you add a proton to it, by definition, it's a different element. It's helium. So if you change the number of protons, you change the element. Now I'm telling you, if you change the number of neutrons, you get an isotope. So that's the easier way to remember it, I think. Yes, the book definition is isotopes, alternate mass forms of an element. But a better way of thinking that is an isotope, it's the same element, but it has a different number of neutrons. And this book, or this example right here is carbon. I'm not going to ask you to memorize that. It's just an example. It's not even from your book. But those give you the three common isotopes of, well, I shouldn't say common, but the three isotopes of carbon: carbon-12, carbon-13, and carbon-14. And let's look. I don't even remember. I mean, I think I do, but I want to be sure. The atomic mass is at 12.01, which tells me most of the carbon in the universe must be close to 12, right? It's not close to 13 or 14, because otherwise the average would be 13 or 14, or maybe 12.5, but it's not. It's 12.01, so that tells me most of it is carbon-12. Again, I said this on Wednesday. I'll remind you again. There's a question like this on the study guide, probably a question, and ask you to basically do some simple math and fill out. So if I say, I don't know, the carbon has 6 protons, its mass number is 12. How many neutrons does it have? So you have to think, okay, 6 plus what equals 12? Oh yeah, 6 plus 6 equals 12. Anyway, any questions about that? To be clear, to clarify things here, what I'm really trying to get at, as far on this slide, is the fact that you need to know what isotopes are. So isotopes, they have the same number of protons, right? They're the same element, but they have different number of neutrons. So isotope, different number of neutrons. Any questions? Honestly, now that I think about it, this is probably the least important of some of the stuff I'm going to teach you. It's still going to be, there'll still probably be one question on the exam. It's probably some of the least important stuff I'll teach you in this chapter, at least as far as biology is concerned. Now, in real biology, when I say real biology, I mean like people doing some really complicated studies. Isotopes are very useful, but you can brain dump this and probably be fine for the rest of the semester. That tells you how important it is for what we learn in biology. All right, so again, there's just just using carbon as an example of isotopes. This is a really off-the-wall example. It's a fake photo, but it's a real condition. I think it's a fake photo. Does anybody know what that's called? When you have extra toes or extra fingers? It's called polydactyly. You don't need to know that. You can look it up for independent work and write about it. And again, I think that's a fake photo, but there are situations when people have have more than they should fingers. So let me ask you this, and I should have asked you this before we got started because I would have been curious to see what the answer was. If I ask you, what is the average number of fingers a human has? You might know that. The average number of fingers a human has. If you had to guess, how about that? I don't actually know the answer. What is it? Like if you were to look at, I have 10. So it looks like you have 10. How many, the average number for humans is what? I don't know. I would guess that a lot of people would guess that, but I would think not. It's probably like 10.0002 or maybe 9.99999, indicating that not everybody has 10 fingers. Some people have extra fingers, some people have missing fingers. Or who knows, maybe the missing and the missing and extra balance each other out and it actually is 10. But the point is, just like, not all carbons have 12, 6 protons and 6 neutrons, right? Some of them have extra neutrons. But most of them in the universe do have 6 and 6, which is why the number is close to 12. Same thing with fingers, right? Just an example of what an isotope is and where we get that number 12.11, right? There is no carbon that has that weight. This is the average of all of them in the universe, as far as we know, which is a good independent work topic if you want. If you want to look that up. Like, how do we know what the average is in the universe? That's lovely. Good grief. Yeah, how do we know that most of them are this and very few are this and very few are this? You can look that up for independent work if you want. All right, a radioactive isotope. No need to write this down because I'm definitely not going to ask you this, but that's an isotope that's radioactive, basically, right? And what do I mean by radioactive in this context? I mean it decays spontaneously. You don't need to know any of that. I'm just going to skip right past it. Because like I said when we started this chapter, the chapter theme for this chapter is radioactivity, and I'm not going to test you about radioactivity at all. Okay, again, every chapter we do has something called the process of science. It really is good to read it. Try to understand it. You know, it is good to think scientifically, but for the sake of saving time, I'm going to always skip it because it'll never be on the exam. I think there are some questions about it on the study guide. So again, it would help you to read it so you can get those questions correct. And if you need help, let me know. There we go. That brings us to the next thing. This is a really important main bullet point. Chemical bonding and molecules. We're going to do a lot of this, and you're going to learn a lot about this in next week's next week's lab. So as far as we're concerned in this course, it's only the electrons that are directly involved in chemical reactions. That's not necessarily going to be a test question, but just keep that in mind moving forward when I'm explaining that this thing bonds with this thing and that element bonds this many times, all this kind of stuff that I'm about to teach you. Keep in mind that as far as we're concerned, it's only the electrons that are directly involved. You really want to go down a rabbit hole, look further into that, because I'm really oversimplifying things. Because really what happens is electrons attack nuclei, and it gets pretty complicated, but we keep it simple in this course. Now, here's some really important stuff. I'm really going to emphasize this next week in lab, but you definitely need to know this. This bullet point right here is very important. Not that I'm going to ask you this, but because to figure out some stuff, I'm going to ask you questions where you have to figure some things out. And to be able to figure things out, you need to know this. It's the number of electrons that determines the chemical properties. Specifically, basically, they want to be full. Like an atom wants to have a full shell of rings, or a full shell of electrons, or a full ring of electrons, if you want to call it that. So as far as we're concerned, when we draw these atoms, we're going to draw the protons and neutrons on the inside, which is the nucleus, like I said. And then you draw little rings on the outside that hold the electrons. And this is also an oversimplification, but it does the trick for what we're doing for Bio 101. So the first ring holds 2 electrons. And as far as we're concerned, all the other rings hold 8. So to give you an example, hydrogen, because I keep talking about it, as you should know, actually you should know that, you don't have to memorize it, but anyway, hydrogen has 1 proton. And because I'm not saying it's charged, that means it also has 1 electron. So is its outermost ring, just does not have, it only happens to be 1 ring for hydrogen, is it full? It has 1 electron. So is its ring full? No. And that just means it's reactive. That's for you guys, that's all that matters. It is reactive because that doesn't have a full ring, so it wants another electron so it can be stable, right? Helium, which is the next one. It has 2 protons, therefore 2 electrons. Is it reactive? Helium. It has 2 electrons. No guesses? Don't feel bad if you're wrong. I mean, I'm teaching this to you, so I don't expect you to know this. Any guesses? Helium has 2 electrons, so is it reactive? Any reasoning? Or are you just guessing? Okay, that's good. I'm glad you guessed. Actually, no, it's not going to be reactive because it's in a ring. The ring holds 2 electrons, right? And it has 2 electrons. Therefore, its ring is full. So it's not reactive. It has 2. It's happy. It's good to go. It has a full ring. I'll go over one more. The next one up, lithium, 3 protons, 3 electrons. So its inner ring is full. It has 2. But then it has 1 more, right? So then we have another ring that only has 1 on it, but it holds 8. So is lithium reactive? Yes, right? Good, because it has 1, but it needs 8. So it either needs to get 7, right? So it can fill up that outer ring, or it needs to give up 1. So then it only has that 1 inner ring that holds 2. Those are just examples. What you really need to know here, again, it's all about this bullet point right here. They want full rings. So if they have a full ring, they're not reactive. If they don't have a full ring, they are reactive. If they're missing one electron, they're going to try to get another electron so they can be reactive. I mean, non-reactive, so they can be stable. If they're missing 2 electrons, they're going to want 2 electrons. If they're missing 3 electrons, they're going to want 3 electrons. This will be really important in the lab because you'll be able to figure it out. I can tell you the proton number, and then you'll be able to figure out how many electrons it has because it's the same thing. And then you'll be able to figure out how many electrons it has on its outer ring. And then from there, you'll know how many times it bonds. So if it has 5 electrons on the outer ring, it needs 3 more electrons to be stable, and that means that thing can bond 3 times. That happens to be nitrogen. Anyway, any questions about that? All right, so this is where we get into chemical reactions. This is why chemical reactions happen. It's because reactions enable the atoms to transfer or share electrons. And I'm not going to ask you the definition of what a reaction is. But this is why they happen, is because of all the stuff I told you right here. These atoms just want to be stable. They want to have full rings. So whether that means they're giving up electrons or taking electrons or sharing electrons, they'll do what they have to do to get that full ring. And that's what, basically, as far as we're concerned, that's what chemical reactions are. Just trying to become stable. And of course, obviously, when that happens, when we give up electrons or take electrons or share electrons, when that happens, the atoms stay close together. And we're going to talk about that moving forward. I'm going to tell you how that happens, so you don't necessarily need to write that down. And when these reactions happen and these atoms come together and stay close together, that's what we call a chemical bond. So any questions about what's on this slide? All right, so the next word for attendance, I'm going to circle it. And again, I'm about to point at it for those of you watching the video. Not of those of you who are live right now, you can just send me the word bonds. But for those of you watching the video, you take a screenshot of me pointing at the word bonds because that is the next attendance word. For those of you live, just send me the word bonds along with the other words. Also, I remind you, they have to be in by 9 a.m. for you guys in person too, right? So if you're sending me the extra words for extra credit, or sending me the words for extra credit, make sure you send them to me by 9 a.m. And for those of you live online right now, make sure you send me the words before 9 a.m. I do this because, every rule is written in blood is what we used to say in the Marines. So I'm really picky about that because people before you have cheated. It's teamwork, right? Someone says, hey, get the words for me and send them to me, and I'll send them in as my words. You could still technically do it, but you have to be quicker about it. So try not to cheat. Also, like I said earlier, I have a Google-generated list of who's online right now. So please, whatever you do, don't send in the words and be like, oh, here's the words. But I know you weren't there. So anyway, no questions about that. Let's move forward. Let's talk about ionic bonds, right? So we know generally what a bond is. We know that these atoms want to have a full outer shell. That's what drives chemical reactions, right? But there's 3 different types of bonds, and this is actually really important as far as the entire semester is concerned. So this isn't trivial. You're going to need to know the difference between ionic, covalent, and hydrogen bonds because that will make a big difference between how molecules interact with each other, which will be really important in chapter 3, and even more important in chapters 5, 6, 7, 8, a little bit of 13. So let's talk about it. First one, we're going to learn about it in no particular order. Actually, this is the order in which the book presents them, but there is no particular, other than that, there's no reason they're in this order. The first one we're talking about is an ionic bond. And that's when an atom gains electrons or loses them. So they're giving up electrons or they're taking them, right? That is an ionic bond. So when that happens, they become electronically charged because as you know from Wednesday, the nucleus is where the protons are, right? And those are positive. And those electrons, as you know from from Wednesday, electrons are negative. So if an atom gives up an electron, what charge would it be? Negative or positive? This is a little bit tricky, so think about it. Take your time to think about it. If it's giving up an electron, what charge would it be? Negative or positive? Good, positive. You got it right. That's good. Yeah, because it's giving up something negative, right? So now it's going to have more positive things, more protons than negative things, electrons. So it's going to become positive. And I know the reason that's tricky is because, usually when you think you're giving something up, then that would be a negative thing, right? But in the case of electrons, it's not. If you're giving up an electron, you're going to become positive. If you're gaining an electron, obviously you're going to become negative. And when that happens, that's what we get this thing right here, which are called ions, hence the term ionic bonds. So let me summarize some things, because your book didn't necessarily do it this way. Let's take a step back before we move forward. I told you if you change the number of protons, you change the element, right? Because an element is defined by its number of protons. If you change the number of neutrons, you have an isotope. And now finally, the third piece of the puzzle, if you change the number of electrons, you have an ion. All right, so let's say he and I know, sorry if you're online, you can't see this. Let's say he and I are atoms, right? And I've got one too many electrons. I want to be stable. He's missing an electron. So he's like, hey, man, can I have your electron? I'm like, yes. Let's say I give him my electron. What charge am I now? Of course, I just asked this in a different way. I give him one of my electrons. Now what charge am I? Positive. Now what charge is he? Negative, right? Because he has an extra electron. Now because of that, and I'm not going to physically do this because I'll get in trouble and it'd be really weird anyway. He's negative. I'm positive. Technically, we're attracted to each other. We'd be like right next to each other, right? That would be an ionic bond. So that's an ionic bond. That's what an ion is. He and I would both be ions at that point, and that's what an ionic bond is. And less important, this is probably a little bit not that important, but technically when that happens, you call that an ionic compound. I probably won't test you on that, but whatever. And to be honest with you, of the three different bonds, ionic bonds are the least important in this course because they won't come up that often. They do come up, but not as much as the other two. So any questions about ionic bonds? All right, I'm going to slow it down a little bit. I do still see some note taking, so I'm not going to jump forward yet. So again, just to remind you, you change the number of protons, you change the atom, the element. Change the number of neutrons, you have an isotope. Change the number of electrons, you have an ion. And that makes them charged, and that makes them attracted to other charged things, and that's what an ionic bond is. Here's a very common example. Sodium chloride, table salt, right? There's the sodium, there's the chlorine. This sodium, you can see its outer ring only has one electron, and I just told you earlier that they need 8 to be stable, right? So that thing can either gain 7 electrons, which is a real pain, or you can just give one up, because once it gives that one up, then it has a full, that ring is gone, and the next ring is already full. Chlorine has 7, right? So it just needs 1 electron. So in that example I was just doing over there, you could say, I was the sodium, he was the chlorine, right? He needed an electron, I needed to give one away. We do that. That makes me positive because I have now more protons than electrons. Makes him negative because he now has more electrons than he has protons. Because I'm positive and he's negative, they're attracted to each other. That's an ionic bond. So any questions, again, about ionic bonds? And of course, that's just an example. I'm not going to specifically ask you anything about sodium chloride. It's not like you need to memorize that. There will be no test question like, which one was positive, which one was negative? No, I mean, if for some weird reason I give you this picture and ask you, then yes, you should know because it's right there in front of you. But I don't think I'll have test questions that easy. But yeah, if I were to give you this picture and say which one's positive, which one's negative, you can just see that has a plus. So you would say the sodium ion is positive and the chloride ion is negative, but you probably won't get that easy. If you download this PowerPoint, you can watch a little video that shows some ionic bonds in action. If I remember correctly, I know there's videos in the pre-lab. I don't remember if they cover this. I'm going to take a look. If the videos in the pre-lab cover this, then we're good. If the videos in the pre-lab don't cover this, then I'm going to share yet another video with you that you can or cannot watch if you want for independent work that shows this in action. But it'll be better than this little animation. Anyway, that's it for ionic bonds. So no questions about ionic bonds? Okay, let's move on to the next one. Covalent bonds. These are really, really important in this course. We're going to talk about them a lot. Let's see. So we know that an ionic bond is when atoms are giving up electrons or taking them. So does anybody want to guess what a covalent bond is? It's almost out of process of elimination. In a sense, there's only, in a way, there's only one left, sort of, kind of. What else could happen other than giving up electrons and taking them? How about this? And I'm going to use H2 as an example. I won't bother you again. Again, I'm a hydrogen. I've got one electron. I need another. She's a hydrogen. She's got one electron. She needs another. But we can't give them up. If I give one up, that's going to hurt me. She'd be fine, but I'd have 0, which would be even worse. So if she has one, I have one. What would we do? What could we do? Yeah, I think I heard it. We could share it, right? And that's what a covalent bond is. Covalent bond is sharing. Atoms share one or more pairs of electrons. So again, ionic bond, you're giving them up or taking them. And therefore the bond is because they're oppositely charged. In a covalent bond, you're sharing them. And this is really important, this next bullet point. So it'll be a test question, and it's really important beyond just the fact, just a test question. Like, you're going to need to understand this concept way later in the semester. The fact that covalent bonds are the strongest bonds will come back when we talk about DNA. But yes, so know that covalent bonds are the strongest of the bonds that you learn about. So again, when you put ions together, like salt, for example, right, we call that an ionic compound. Well, when you put molecules together in a covalent bond, we call that a molecule. Right? It's a molecule. And I'm probably not going to ask you what a molecule is, but now you know what it, I'm sure you probably already knew, but when you hear me use the word molecule, now you know what it is. It's when 2 or more atoms are together because they're sharing electrons. And again, it's the same purpose. They're still trying to do the same thing. They're trying to fill the outer shell. But of course, in this case, they share the electrons. They don't give them away or take them. And there's reasons for it that if you took a chemistry class, you'd probably get into, but we don't even do that in this class. You just need to know that's what happens. If you want to know why, like why would it share instead of give one up? If you want to look that up, go ahead. But I'm just asking you to trust me and know that sometimes they share them, sometimes they give them up, sometimes they take them. When they share them, it's called a molecule. It's called a covalent bond. And formaldehyde is a famous example. You don't need to know that. That's just, again, just an example and just some meme that I found on the internet. I was not looking for it. So any questions about covalent bonds? You're going to learn all about covalent bonds in next week's lab. As a matter of fact, there's a whole section where you're supposed to draw molecules. And I'm going to teach you how to do that next week's lab. But if you already happen to know, feel free to go ahead and do it. Because obviously when you're done with lab, you can leave lab. So if you want to work ahead, feel free. But anyway, if there's no question about covalent bonds, let's move forward. Or sorry, I'm going to give you an example. Oh, this is good. I remember doing this now. So this is really good. This will help you understand what you're going to do in lab next week. So pay close attention to this. So carbon. In the lab, you're going to have to fill out a table. And I'm going to tell you to look up carbon. When you look up carbon, I'm going to tell you its atomic symbol is C. So you can look it up right there, see the C, and I know you guys can't see, but it has a 6 on top of it, right? Its atomic number is 6. So in that little table that you're going to have to fill out, it's going to say, how many protons does it have? And the answer is 6, because the atomic number equals the number of protons, right? It has, if its atomic number is 6, it has 6 protons. Now, this thing is not charged, right? The way this one I'm presenting to you, it's not a positive carbon, it's not a negative carbon, it's a neutral carbon. So if it has 6 protons, how many electrons must it have? It's not charged. So if it has 6 protons and it's neutral, how many electrons must it have? If it has 6 positive things, how many negative things must it have to neutralize itself?
6.
Good, 6. I just have a microphone. I'll put it up to you. Yes, 6 electrons. We know because it has 6 protons, therefore it must have 6 electrons because I didn't say anything about it being charged. Therefore, if we were to think about it, again, the first ring holds 2 electrons, right? So we know there'd be 2 on the inner shell. So that means there's 4 more electrons, right? Because 2 plus 4 equals 6. So that means that next shell, so the inner one holds 2. The next one has 4 on it, right? Because 2 plus 4 equals 6. So that means the outer one has 4. Does anybody remember how many it needs? I don't know. I just told you, so don't feel bad if you don't remember yet. But you will need to remember eventually. The outermost holds how many electrons? 8 total, right? So it has 4, needs 4 more. Therefore, it can bond 4 times. And that's how that works. And that's what you're going to need to, that's the thought process that you need to do next week for lab and at least once for the exam. I'll give you an element, I'll give you its atomic number, and then from there, you can figure everything else out because the atomic number equals the number of protons. And if it's not charged, that also equals the number of electrons. And then once you know the number of electrons, you can figure out how many are in the inner shell, how many are on the next shell if there is another shell, how many are on the shell after that if there's another shell. And then you can figure out how many electrons it needs to be full, which is the same number as how many times it can bond. So to help you out again, and I'm going to reinforce this on the next week. Technically, these numbers are always going to be the same for lab, right? The atomic number equals the number of protons. The number of protons, if it's not charged, will always equal the number of electrons. So those numbers will always be the same for lab, and these numbers will always be the same. How many electrons does it need? Well, that's how many times it can bond. So any questions about that? So don't memorize all this information, right? When you're studying, don't make little flashcards that say, you know, carbon, and then you flip it over and it says 6 electrons. Or carbon, 2 electrons on the inner shell, 4 on the outer shell, right? There's nothing to memorize here. What you need to understand is how to work this process out, right? You need to be able to, if I were to give you the atomic number, you should be able to figure the rest of this out from that. Because I might give you some wacky one that we don't talk about, you know, in class or in the book or in lab. For the exam, I might give you something off the wall. Because again, it is a pretty simple process once you're used to it. Anyway, any questions about that example of carbon? All right, here's another example. Again, formaldehyde. And there's definitely nothing to memorize here either. Again, I'm not going to ask you I'm not going to show you this picture and say, what molecule is this? Or I won't say, draw me a molecule of formaldehyde. I won't do that. This is just an example. Another thing I want to do is say, you know, give you all these pictures and say, which one's the electron configuration? Which one's the structural formula? Which one's the ball and stick? Which one's the space filling? You don't need to know that. I guess the only point here that I'm trying to make is there's different ways of drawing molecules. This is the one you're going to do. So be familiar with this one. The structural formula, that's what you're going to do in lab next week. So you're going to learn all about that next week. Yeah. I don't know. If you go home for the weekend and you tell them, hey, look, I figured out how to draw. I learned how to draw formaldehyde, and you draw on this. And then they're like, no, and they show you some picture of this. Now you just know. They're not wrong. You're not wrong. You're just looking at different things. Because I know that's what people do on weekends, right? You talk about formaldehydes and different ways to draw it and show it. So now you know. Any questions about that slide? All right. Again, if you download this PowerPoint, you can watch a video about covalent bonds. It's an animation that shows it in action. That's actually the same example I just used with us. I was a hydrogen. You were a hydrogen. We were sharing electrons. You can watch it if you want. I'm going to find a better video for you. If I haven't posted it already, I will share it with you on Google Classroom. And again, to remind you, when I share it on Google Classroom, read the whole announcement. Please read the announcements. Yes, some of them are less important than others, but please read them. And usually the ones where I say reply to this for extra points, you know, for independent work points, usually those are the important ones. And again, not everybody's doing it, which tells me not everybody's reading your announcements. It'll help you, I promise. Anyway, we'll get off this soapbox and land right back here. We're done talking about ionic bonds. We're done talking about covalent bonds. Let's talk about the last type of bond that we will discuss, which are hydrogen bonds. Before I can tell you what a hydrogen bond is, I have to give you a little background information. First of all, let's talk about water. As you already know, I assume you already know this, water is H2O, meaning that it's 2 hydrogens, 1 oxygen. What you might not have known, and you probably knew this too, was that those 2 hydrogens are each attached to an oxygen, right? So it's not like hydrogen, hydrogen, then oxygen. It's one center oxygen with 2 hydrogens attached to it. Now, what I haven't told you, and what I don't expect you guys to know yet, is this new information, is that water is a polar molecule, meaning that it has an uneven distribution of charge. So you need to know what a polar molecule is, an uneven distribution of charge. And the reason this is, and there's questions about this on the study guide, the reason it's a polar molecule, like it says in the bullet point above that, the electrons are not shared equally. It's really hard. This is gonna be It's going to be a little bit tough. I would hate to put you on the spot. I'll only give you a couple seconds. If you can't do it, that's fine. But anybody over there who can read the periodic table, can you tell me what oxygen's atomic number is? And I'll give you a hint. It's up towards the top right. 8. Good. Its atomic number is 8. Meaning it has 8 what? By definition, if its atomic number is 8, it has 8 what? Great. Protons. And again, you will need to know that. Not that oxygen has 8 protons, but that the atomic number equals the number of protons. Yes. So it has 8 protons. It has 8 positive things. So again, you guys over there, I hate to put you on the spot. Of course, you guys might all know this because I've said it so many times. But how many, or what is the atomic number of hydrogen? I think someone said it. Yeah, 1. Its atomic number is 1. So it has 1 what? Proton, yes. Oh, that's so horrible. This thing won't let me draw. All right, so this thing has 1 positive thing. This thing has 8 positive thing, or 1 positive thing. This thing has 8 positive things, right? So this one's a little bit positive. This one's a little bit positive. This one has a lot of positive things. Now, electrons are attracted to protons, right? Now, if you're an electron, what are you going to be more attracted to? The hydrogen or the oxygen? If you're an electron, you want to hang out at this place that has the 1 positive thing or the 8 positive things? Yeah, the 8 positive things, right? And that's why the electrons are not shared equally. Yes, those are covalent bonds, but the electrons are hanging out more over here because they're attracted more to the oxygen than they are the hydrogen. So that's what makes it a polar molecule. That's why the electrons are not shared equally. So this molecule, let me undo what I did there. That won't let me. Anyway, a water molecule, not that you need to know this. You don't need to go into this much detail, but or remember this much detail. But basically, this part of a water molecule is a little bit more positive now, and this part's a little bit more negative. Not completely. It's not a complete charge. But if you were to look at a water molecule, if you were to hold a water molecule next to a magnet, like the negative side of a magnet, it would go like this. Like if that were the magnet, it would be attracted that way. Because this part is a little bit more positive because the electrons are hanging out here. And again, you don't need to know that much detail. The point is, again, the electrons are not completely or equally shared. Therefore, there's a partial charge on the molecule. And that's what a polar molecule is. And because there's these partial charges, that's where we get hydrogen bonds. So in a sense, hydrogen bonds are a lot like ionic bonds because it's the charge difference that's attracting them, right? So a sodium and a chloride are attracted to each other because one's positive and one's negative. With water molecules, it's sort of the same thing, except they're not completely positive and completely negative, but there is a slight positive charge here and a slight negative charge. So because of that, they are slightly attracted to other things that have a charge. And that's what a hydrogen bond is. Before I move forward to show you these things in action, I'll give it a second to let you guys write some notes. But also, I'm remembering some questions that are definitely on the study guide and will probably be on the exam. They're 2 separate questions. The questions are shuffled up, so they probably won't be right next to each other. But one of the questions is going to say, and let me back up, and I'm sorry. I'm going to back up. One of them is going to say, what holds a single water molecule together? And the answer is covalent bonds, right? That hydrogen is covalently bonded to that oxygen. That hydrogen is covalently bonded to that oxygen, right? So a single water molecule is held together with covalent bonds. The next question, probably somewhere else, or the other question, is going to be, what holds multiple water molecules together? And the answer is hydrogen bonds. So this thing is held together with covalent bonds. This thing is held together with covalent bonds. This thing is held together with covalent bonds. This thing and that thing, all individually held together with covalent bonds. But what holds them together? What holds this thing to this thing, and this thing to this thing, so on and so forth? Those are hydrogen bonds. And that's all a hydrogen bond is, right? It's because it's a little bit like an ionic bond because you have a positive attracted to a negative, right? Except these things aren't completely positive or completely negative. Therefore, it's just a hydrogen bond. So any questions about what a hydrogen bond is? And hydrogen bonds will be important later in this chapter, and then again later in the semester. All right, if there's no questions, we'll move forward. Actually, let me stop here. I should have put this in writing like I did for covalent bonds. Actually, I'm not going to try to write with that. It's goofy. But covalent bonds are the strongest bonds, right? The other thing you need to know is that hydrogen bonds are the weakest. So if you're taking notes, write that down since I didn't, and I apologize. You already know that covalent bonds are the strongest. That's already written in the previous slides, but what is not written down, the hydrogen bonds are the weakest. And again, that will be very important once we start talking about DNA. Okay, moving forward. So now you already know a little bit about chemical reactions because I already told you earlier, chemical reactions is basically, atoms coming together because they want to fill their outer shell of electrons, whether they're giving up electrons or taking electrons or sharing electrons, right? So now we'll just dive a little bit deeper into chemical reactions. Your book points out that cells constantly rearrange molecules, break bonds, and form new ones. So right now in your body, you're basically like a chemical vessel, right? Just a bunch of stuff happening. You're breaking bonds, you're making new ones, you're changing one thing to the other. And what do we call changes in chemical compositions of matter? Those are chemical reactions. I might put a question mark next to this, not because it's questionable, because I'm not sure if I'm going to ask you that on the exam or not. I'm not too big on definitions, especially this one. But yeah, that's what a chemical reaction, that's technically what it is. It's the changes in the chemical composition of matter. The chemical composition, even though you don't need to go this deep on the exam, just so you know what this means is, if you were to put like these two things, put hydrogen peroxide in some, I'm going to use a different example. I won't even get that deep. I might get that deep later. We'll cross that bridge when we get there. But some things you definitely need to know, not because I'm going to ask you, but because I'm going to use these terms a lot. You need to know what a reactant is and a product. The reactant, that's the starting material, and the product are the end material. You definitely need to know what these things are. I'm going to use this term a lot, not just this chapter, but here and there throughout the semester, we're going to use those terms. Now, in this class, it's not always the case when you take real chemistry, but in this class, reactants are always going to be on the right. Products will always be on the left. And, well, this is the case with real chemistry, the arrow is always going to point towards the products. Of course, it does get a little bit more complicated in real chemistry because a lot of times you'll see the arrow go both ways because technically chemical reactions can go both ways. As far as we're concerned in this class, and you do need to know this is important, reactants will be on the left and they will point towards the products on the right. Reactants are what we start with, products are the end material. If you were to think about cooking as a chemical reaction, and I'm not good at baking, so forgive me because I know this is going to be wrong, but if you were to say something like, the reactants are eggs, flour, sugar, and chocolate chips. And then you have a little arrow to the right. And the products, chocolate chip cookie, right? Are there any questions about what a chemical reaction is or what the reactants of the products are? Very important concept. Again, not because I'm going to test you on it, but because you need to understand that when I explain things later. And here's also another really important concept, more philosophically than for understanding what I'm going to teach you later, but chemical reactions only rearrange matter. Nothing is created or destroyed. You cannot create or destroy matter. You can create or you can destroy, like in this case, we can destroy some hydrogen peroxide, but we haven't destroyed matter. We've just rearranged the atoms. We rearranged the stuff that made up that hydrogen peroxide. This is just an example, so please don't think you need to memorize this equation. But here we have two molecules of hydrogen peroxide. Hydrogen peroxide happen to have two hydrogens and two oxygens, right? Each one of them has two hydrogens, two oxygens. You ever poured hydrogen peroxide on a wound? Has anybody ever done that? Yeah? What happens when you do that? It bubbles, right? And this is the reason why. This is what's happening. The chemical reaction is turning it into water and oxygen. So what are bubbles? Bubbles are gas and liquid, right? So there's the liquid, there's the gas. But anyway, the point here is, yeah, we destroyed a hydrogen peroxide, or two hydrogen peroxide molecules, but we haven't destroyed matter. We have 1, 2, 3, 4 oxygens here, 1, 2, 3, 4 hydrogens. It goes through the chemical reactions. We have 1, 2, 3, 4 oxygens, 1, 2, 3, 4 hydrogens. Matter was not created or destroyed. It was simply rearranged. Anyway, any questions? Entire slide. Okay. Forward. Yes, to the thing we're going to talk about now that we know about basic chemistry is water. This video I know is in the lab, next week's lab for the pre-lab. You're not required to watch it, but I highly recommend it. Even if you don't feel like watching it and answering the questions for extra credit, at least watch it. It's a short video. It's going to explain what I'm about to explain, but they do a better job of it, and there's better animations. So please watch it. Anyway, let's talk about water and life. Your book points out that life began in water, and it evolved there for 3 billion years before it came to land. You don't need to know that number. It's just an introduction. So it's like, before I teach you about water, I'm going to kind of tell you why you're learning about water. Why is it so important? Who cares? Well, I'm about to tell you. So yeah, life was there 3 billion years before it even came to land, which is actually interesting. Speaking of which, and this is slightly off topic. There's another independent work topic. My brain works this way. Sharks are older than trees. So sharks have been around on Earth longer than trees have, which isn't exactly what we're talking about. But when you talk about life going from ocean to land, yes, sharks are older than trees. Just something to think about if you want to for independent work. If you want to look that up, like just think about random things that you know of, random species or types of organisms, and look up which one's older. You might be surprised. But anyway, yes, life began in water. Therefore, it's still tied to water. This is why, like when things, we search for water on Mars, for example, because if, once we found out that there used to be water there, then that means there at least used to be a possibility of life. Here's one number you do need to know. That's why I put a little star next to it. Cells are about 70 to 95% water. Of course, that depends on the species, and even within your body, it depends on what kind of cell we're talking about. We're talking about a fat cell, a bone cell, a brain cell, blood cell. But yes, know this number. It will be on the exam. 70 to 95% water. So that is the one thing on the slide that you need to know for the exam. The rest of it is just an introduction to why we're about to talk about water. Why is it so important? The next word for attendance. And if you're watching the video, you need to take a screenshot of me pointing to it. The word is earth. The rest of you can just email me the word earth along with the other ones sometime before 9 a.m. Yes, the above is the major reason earth. Why? What is that? What is it about water that equals life? And that's what we're about to talk about. All right. I'm going to put an X to this, only indicating that it won't be on the exam. Again, this is kind of like I'm introducing you. I'm bringing you up to what you need to know. So to get there, I'm going to let you know that it's the polarity and the hydrogen bonds of water that explains most of its life-supporting properties. Not that you need to, I'm not going to ask you that. It's just something to keep in mind. As I'm teaching you this, just keep in mind the fact that it's a polar molecule, the fact that it hydrogen bonds, that's why it does most of the magic that it does. There's 4 properties I'm going to teach you about. But again, there's no need to write this down yet because we're going to talk about them each individually. The first one is the cohesive nature of water, and I'll explain what that means if you don't know what that means. The next will be the ability to moderate temperatures, which is pretty straightforward, but anyway. The biological significance of ice floating. I'm sure you guys know that ice floats, but we're going to talk about why that's important for life. And then finally, we'll talk about the versatility of water as a solvent. You might not even know what a solvent is, but again, I'm about to teach you. So that's what we're about to talk about. There's no need to write those down yet. The cohesion of water, that's the first one. So before I tell you, does anybody even know what that means? Cohesion. Forget that we're talking about biology and the cohesion of water. If I were going to say these things that thing is cohesive, what does that mean? Cohesive, cohesion. Either one you want to define, cohesion or cohesive. What does it mean? Any guesses? Perfect. It's sticking, right? It's when stuff sticks together. In this case, we want to, obviously, because we're talking about water, we point out that water molecules stick together. as you already learned earlier, because of those hydrogen bonds. So that's nothing new. I just taught you that. Water molecules stick together because of hydrogen bonds. But now I'm telling you that that is called cohesion. Stick together. Of course, technically, when it's the same molecules, that's called cohesion. Now, if I were to slap I shouldn't say slap. If I were to get a Post-it note and stick it to her forehead, again, I'd probably get in trouble for touching her. But that would be called adhesion, right? Because those are different molecules. But when it's the same things, it's cohesion. Not going to ask you to know the difference, but now you know. So your book gives one example of why this is so important, and it's trees, right? Obviously, we wouldn't have life as we know it on Earth without trees. And trees wouldn't be around without cohesion. And let's talk about why. Oh, it's 8:49. You know what? You know the definition of cohesion. So when we come back on Monday, I'll give you the example, the thing for leaves. And the last thing, and you guys, if you're online right now, not if you're watching the video, or you're here, you don't need to worry about this. I'm going to make it a little bit trickier for those of you watching the video. If you're watching the video, your last thing to do is not an attendance word, but like the video and then send a screenshot that shows that you liked the video. There we go. All right. Any questions? All right. So for those of you who wore red, I think I have you down as wearing red for your little extra credit. And if you want to, we can stick back and take a picture again for extra credit. Otherwise, I'll see you guys all on Monday.